I wanted to talk to you today a little bit about exploration, and I'm doing that because I think we have largely a room of geoscientists here. How many people are geoscientists in the room? And that includes like oceanographers. I mean, just everybody that's here. Who's here for the AGU conference? All right, so we'll cover most of the folks. I want to talk a little bit about exploration, and then I'll follow that up with some discussions about my space shuttle missions and what it was like to be in space and some of the training that we do to get there. Mike gave me an introduction so you know all this stuff, but I've got a few training slides up here to sort of show the different experiences that we have before we go into space. And over 90%, probably 99% of the work that we do as astronauts, we actually do on the ground. I've been an astronaut since the year 2000, and I joined with this group of folks, Group 18. We were called the Bugs. The reason we're called the Bugs is because of the Y2K bug, right? So this was our group, and since our class joined in 2000, there's been two more. There was a class in 2004. In 2009, and there's going to be another selection in about a year and a half. And we'll talk about what that means for the space program as we go along. But right now, there are about 65 current astronauts in the U.S. astronaut program. So, and I'm talking today about exploration just because of the audience that we have here, and because that's what we do as astronauts. We explore. We believe in exploration, and ultimately we believe in exploring to the point that we can live off of this planet. That's our ultimate goal. We explore the surface of the Earth, and many of you here explore the surface of the Earth. We explore underwater, the underwater environment. As astronauts, we do both of those things. We look for ways to train, to explore these things, and find analogs to environments that we might find in space. We also explore the Earth from space, and many of you may do that remotely through satellite work as astronauts in the past up until this year. So historically we've done that with the Space Shuttle, and we did that up until this year when we landed Atlantis for the last time. My flight was STS-134, was on Endeavour. That was Endeavour's last flight to space. So this is how we used to do it. Now we currently fly with the Russians on the Russian Soyuz rocket. And our destination as astronauts is the International Space Station, which is flying 220 miles above the planet continuously. It's been there since the year 2000. We have had astronauts on board, and right now there are 6 people on board that vehicle orbiting the Earth. We also explore the cosmos as humans, and one of the ways we do that is with the Hubble Space Telescope. And I had the good fortune in 2009 of being able to go and see the Hubble Space Telescope and make some of the final repairs on that satellite. So one of the things we do, we fly T-38 jet aircraft. So we look for ways to train together to prepare us for space flights. This is a high-performance environment. We work together as a team. We're making decisions in this environment that have life consequences. So we have simulators that we work in, and we also try to find real environments where the decisions we make matter and could potentially kill us. So this prepares us for spaceflight. We think this gets us ready because we're constantly making decisions in a high-stress environment and trying to make the right decisions. It's the same scenarios that we face when we actually fly on space vehicles. We have to make real-time decisions that matter, that are important, and could have serious consequences. So we look for analogs. We also look for ways to train together as teams, as groups of astronauts, again, living in environments that we're not comfortable with, survival situations where we have to work together as a team. We may not know each other that well. We may have not trained together very long, but we're thrown into situations where we have to survive and make it through and complete our objectives in the time that we're given. So we work in cold environments. We work in hot environments. We work in underwater environments. This is the Aquarius subsea exploration station. It's off the Florida Keys. It's about 60 feet below the surface. And every few years we send groups of astronauts to live in this underwater vehicle, and it's about the size of a school bus. And so we live here for 2 weeks, just like we would on a space mission, and try to carry out objectives and tasks. And we look for ways to simulate activities that we might do on another planet. As a geophysicist, I've tried to contribute to the exploration of planetary environments by testing seismic equipment and looking at ways to miniaturize, reduce volume and mass, and look at the logistics involved with astronauts going to another planet. The last time we were on a body orbiting the Earth, the Moon, we did some seismic work, and so when we go back there, we're going to do the same thing. We're also going to do other geological observations. So we try to find places that are analogs to what we might do in space, and also look for ways to test equipment and hardware, and look for the state-of-the-art components that will allow us to achieve what we desire on the surface of those places with the most efficiency, because it costs a lot of money to launch weight into space. So the lighter we can make things, the easier we can make them to operate, the more things we can do telerobotically or whatever, that helps us to optimize the work we do and the efficiencies as astronauts in other places. The ultimate goal for us is to go back to the Moon, possibly asteroids, and eventually onto Mars. And so that's what we do as astronauts. Those are ways that we train to get into space and prepare ourselves for those environments that we're going to work in. And I can tell you that geoscientists have always been a part of that and will continue to be a part of it. 2 days ago, for the first time in the history of the human space program, this was a big deal for us, there was 2 geophysicists underwater at the Neutral Buoyancy Lab at the Johnson Space Center. This is myself on the left and Alex Gerst, who is a recent astronaut with the European Space Agency. He's a volcanologist, geophysicist from the Karlsruhe Institute of Technology in Germany. So he's a German, he's a European astronaut, and we, the 2 of us, were together underwater in the pool training for a space flight, preparing Alex for his eventual flight to the International Space Station in a few years. So we thought that was really important, and we made a nice little picture here, underwater geophysics, for lack of something more inventive to write on that. But it was important to us, and we recognize the significance of this, that there have been geoscience astronauts in the past, but we're seeing more and more, and each time we have a selection, earth scientists, atmospheric scientists, geoscientists are being considered for these positions, because ultimately we believe as a species, as humans, that we're going to live off of this planet, and we need to have scientists that are capable of doing the assessments and the science we do when we get there. So this was a big deal for us, and I hope everybody appreciates that event for Alex and I. So I'm going to tell you quickly, if I can, about the 2 space missions that I flew into space. And the first was STS-125, the final servicing mission for the Hubble Space Telescope. This was our vehicle, Atlantis, as it was on its way to the Space Shuttle launch pad. We launched in May of 2009, so it was May 13th, 2009, after many delays. I trained for this mission along with my crew for 3 years in preparation for the final work that we were going to do on the Hubble Space Telescope. And this is the crew that went into space. 3 of the crew were veterans, and 4 of us were rookies. Scott Altman was our commander. This was his 4th flight into space and second to Hubble. Greg Johnson was a rookie pilot for us, his first flight into space to Hubble. Megan MacArthur was a rookie and a member of my class of 2000. She was our robotic arm operator. Mike Good, also a member of the class of 2000, his first flight into space, and he flew a second time to the International Space Station on STS-132. Mike Massimino, this was his 2nd flight into space and his 2nd visit to the Hubble Space Telescope. And lastly, John Grunsfeld, we called him Mr. Hubble. He had been to the Hubble Space Telescope 2 times before. That was his 3rd time to the telescope, fourth flight into space. And it was great as rookies to have those veterans on board with us to prepare us for what we needed to do when we got to the telescope and all the work that was required. So this was our destination, Hubble Space Telescope. And the Hubble telescope is floating or orbiting the Earth about 300 miles up. So it's approximately 100 miles higher in orbit above the planet than what the International Space Station is. So when you go to the Hubble Space Telescope, you don't see the space station, you don't know where it is. Hubble's orbiting around the equator of the planet, The International Space Station is orbiting at latitudes as high as 51.6 north and 51.6 south. So we see a lot more of the Earth from the space station, but from the Hubble Space Telescope, because we're 100 miles higher, we have a completely different perspective on the Earth. It actually starts to look smaller to us, and you can see more of the arcs or the edges of the Earth when you're orbiting the planet. But this is where we're headed, and that's how we found Hubble floating above the planet. Once we got there, Megan MacArthur used the Canadarm1, the robotic arm that exists on all the space shuttles, to reach out and grab Hubble. It was Scott Altman's job and our pilot Greg Johnson's job to pull up right next to Hubble, nice and slow, so that Megan and basically arrest the orbital motions, the relative motions between the two vehicles. So we were essentially just hovering right next to it. And then Megan used the robotic arm to reach out and grab a hold of the telescope and then place it in the back of the Space Shuttle payload bay. So it's not like we docked with it. We simply rendezvoused and then used the robotic arm to grab a hold of it. Once it was there, it was sort of like having something in the trunk of your car or the back of your pickup truck. And in order to get to it, we had to put on our spacesuits to go outside of the airlock and do the work, which was great for the people inside, because when you have 7 people in space inside of a space shuttle, which is about the size of your kitchen, with 1 bathroom, it's really great when 2 guys take 2 really bulky suits and they put them on and they go outside, because you gain the space of like 4 people inside that volume. So it makes it hard to get back in too, because they don't want to unlock the door. You know, you're like, let me in. And they say, we're not letting you in. So anyways, we did 5 spacewalks over the course of 5 days when we were in space on this mission. We did them back to back. That means every day a different group of individuals went out. So my partner was John Grunsfeld, the veteran Mr. Hubble, and then the other team was Mike Massimino and Mike Good. And so while 2 people were outside, the other 2 spacewalkers were inside quarterbacking the EVAs or the spacewalks and making sure that the crews outside knew what they were doing next. So we did those back to back. So every day that when we were done with the first one, we reset everything, changed the suits out, exchanged the tools, make sure we had everything ready for the next day, the choreography for the next day, and then the next team went out. And then when they came back in, we switched it all around, changed out the suits and tools, and then our team went back out. So we did that 5 days in a row. And normally when you go to space, you have a little bit of a break in between because there's a lot to do, especially when you go to the space station. But for a Hubble mission, all we were there for was to fix the telescope, and that's all we did for 5 days. Each spacewalk lasts about between 6.5 and 8 hours. So when we get in the suit in the morning, we wear it for the next 8 hours, if you include the time it takes to suit up and get ready to go out the door. And when we come back in, you know, we don't take a break until we come back in, and we go outside with a couple liters of water and a diaper. That's what we do when we go out in space, because there's no bathrooms out in space. Obviously, we can't take a break. So, anyways, we did 5 spacewalks. I was lucky enough to get to do 3 of them on Hubble, and the view of Earth from space is incredible. It's incredible from Hubble. The day and night cycles, this is an example of us transitioning from nighttime to daytime. So we work right through the darkness as well. We see 16 sunrises and sunsets every day when we're in space. So over a 24-hour period, we see 16 of those. So if you're afraid of the dark, when it's dark, you just wait about 35 or 40 minutes and suddenly it's light again, and then everybody's happy. But the funny thing about this mission, for those of you who followed the mission, we had some challenges. And we came to the conclusion after about 3 days that all the bad stuff was happening when it was nighttime out. And we don't know why, but every time it got dark, there was always this fear while we were on the spacewalks that something would go wrong, that a tool wouldn't work, or something would get stuck, or maybe we'd lose something. Fortunately, in spite of all the drama that did ensue during the mission and the spacewalks, we were successful in the work that we did. And there was quite a lot of it. So for the first time, this is a view of taken from a camera by one of the spacewalkers, probably Mike Massimino, because he was on the spot when we did this. This is the STIS instrument, and I've even forgotten. I don't even want to try to remember what the acronym is. Anyways, one of the instruments inside Hubble, it's about the size of a refrigerator. This was the first time in the history of the space program that we have actually done what we like to think of as brain surgery on the telescope. We we removed the covers on the front of the computers that were inside this box and actually pulled out the cards and replaced the cards. We've never done that as astronauts before, but the reason we were able to is because of the advancement in technology, the ability to generate tools, specific tools that are designed for the task, and of course the fact that we spent 3 years preparing for this mission. So with all of that work, it finally led up to us having the capability that we've never had before, which is getting right inside the telescope and pulling out the cards that make up some of these components. So after 5 spacewalks, John and I, you can see we're smiling here, not just because it's fun to be in space with a spacesuit and the view's great, but because we successfully completed those 5 spacewalks, and the work that we set out to do, we hope has now prepared Hubble to last for another 5 to 15 years. And I say that because one of the things we put on the telescope was new batteries. And that's one of the reasons we launched into space, was because Hubble's batteries were dying. It was losing its ability to recharge its batteries with the solar rays. So we replaced the batteries, and they're certified for 5 years, but we're hoping that they're going to last for 15, as long as the rest of the instruments keep working as well. We hope to see science coming out of Hubble for a long, long time. And that's why we're smiling. And I like the photo because the reflection of the Earth is here in our visors. Anyways, it was a lot of fun. After 13 days in space, 3 of which were spent just orbiting the planet, waiting to come home because it was so stormy and cloud-covered at the Kennedy Space Center that we couldn't return back to Kennedy, we landed at Edwards Air Force Base in California, much to the chagrin of our family who was waiting for us in Florida. We landed in California, so we didn't get to see them right away, but it was an amazing flight, and one of the most impressionable moments of the whole space flight, of this first space flight, for me, was the day that we landed. It wasn't, I mean, there were a lot of moments in space that I remember and some things that'll stick with me forever, but the one thing that will always stick with me was when we landed in the California desert and the crew came to extract us from the vehicle and they cracked the hatch. The exchange of air between the desert and the spaceship was immediate, and I could suddenly, it was like I could suddenly smell the desert. I could smell the dirt. I could smell the vegetation. I could smell the water. I could smell everything on the planet. And it almost overwhelmed me that we were home, that I was back on the planet. And it was the smell. So as soon as I smelled that, even though I was still inside the shuttle, I could see the whole desert in my mind. It was amazing. So Earth really is our home. You know, that's what's so amazing, is that when you're in space looking at the planet, you think, that's the most beautiful place you could possibly be. And we're up here in space and we're having a good time, but that's really where you want to end up. And that was one of the moments that brought that really true for me. So, and this is the reason we went to fix Hubble. This is one of the reasons, because Hubble has taught us more about the universe than virtually any other instrument, and hopefully nobody will take offense at that, but it's one of the most amazing scientific instruments that we've ever built as humans, because it returns images of space that we didn't even know existed. I mean, these are star fields in space that we can't see that with our naked eye. We don't even really know that stuff is out there, but it's out there. And these images represent such a small patch in the sky. You could take your thumb and hold it up at night, and you would cover up the space that this is representing. So this is everywhere in space, and that's one of the magical things about Hubble, is that it's taught us so much about the universe and so much about the wonders out there, that we really look forward to many, well, hopefully at least another decade of science from Hubble. And now that some of the funding has been appropriated, we look forward to the James Webb Space Telescope taking on some of the work that Hubble's done over the years. It's a different type of telescope, but it will have the ability to look even farther into our past and what we think is closer to the beginning of the universe. Okay, so that was the nutshell version of the Hubble Space Telescope servicing mission in 2009. And now I'm going to talk to you about STS-134. And this mission was a mission to the International Space Station. We launched on May 16th, 2011. So it was 2 years and 3 days since my first mission that I launched on the second one. I got very lucky. I got lucky because Hubble flew so late, with like a year delay sometime late in our training. And then with the end of the shuttle era coming, we knew it was coming. I was very fortunate, myself and one other individual on our crew were fortunate enough to fly to space station and get that one last experience. And I can tell you that the only thing that was the same about these two missions was the fact that they were in space, because otherwise they're completely different, and we'll talk about some of the differences. This is the crew of Star Trek. No, this is our crew. Mark Kelly was our commander. Everybody's very aware of who Mark Kelly is. He's been in the news a lot, just released a book, which is an interesting read. And, but we were really proud that Mark was with us and was able to rejoin us after what happened with his wife, Congresswoman Gabrielle Giffords. And we're all very pleased that she's doing well and making a strong recovery. So this was Mark's third mission to space, to the space station. Greg Johnson. This is another Greg Johnson. I don't know if you guys remember, I said on the first mission I flew with Greg Johnson. So this is trivia. Who was the only astronaut that flew with Greg Johnson twice that's not the same guy? It's me. I'm the only one, because both of my pilots were named Greg Johnson, but they're two different people. So anyways, this is Greg Johnson, our pilot. This was his second mission to the International Space Station. And to his left is Roberto Vittori. He was our Italian astronaut flying with the European Space Agency and the Italian Space Agency and Italian Air Force, and we were pleased to have him on board. Roberto was one of our prime robotic arm operators. To his left is Greg Shamatov. Greg Shamatov had flown to the International Space Station once before on the Soyuz rocket and spent 6 months in space. So this was his second time to space station, but his first space shuttle mission. To Mark's right is Mike Fink. Mike Fink is a mission specialist, also a spacewalker. He holds the record of American astronauts in space with 382 days. So he's lived on the space station for 2 6-month missions, and both times he flew on the Soyuz spacecraft. So this was Mike's third time to the space station, but it was his first time flying on a space shuttle. And then you know who I am, hanging on the side. First mission to ISS. This was our launch, a great daytime launch. That part about the mission was very similar. The launches were very much the same. The shuttles feel a lot alike. It's a wild ride going into space. It's about an 8-minute ride. So we go from 0 to 17,500 miles an hour in 8 minutes. And we accelerate off the pad at about 2 Gs. And when as we get close to the last 2 minutes of space flight, we accelerate to 3 Gs. And what that feels like is that somebody put a dishwasher on your chest or a refrigerator and just left it there while you're laying on the ground. But fortunately, at the end of 8 minutes, when the engine's cut off, all of that goes away and everything immediately starts floating and your brain starts spinning at the same time. But that doesn't last very long, fortunately. We launched on a cloudy day with the cloud deck well, for the launch, I think the people on the ground only saw us for about 20 seconds. And then we blasted through the clouds, and this is just a great shot of us just rocketing into space at probably Mach 5 by the time we've seen this picture on our way into orbit. And I showed this picture already. This is the International Space Station, and it's beautiful to see this in space. It's amazing when you get close to it to think that we've actually built this. None of the components that were assembled in space, well, very few of them, were ever mated together on Earth. So each component, and many of them were built by different countries, each component was built on the ground, some of them in a different country. They'd never seen each other before, but when we get to space, we attach them all together. So it's a real testament to the engineering and the science and the work that went behind the assembly of this wonderful craft, that everything fits together and it works well. The total dimension of the space station, I think many of you have heard, is about the size of a football field or 1.5 football fields. And the crew lives in the center section, the volume right down the middle. And that's approximately the size of a 3,500 square foot home or 4,500 square feet, about a 5-bedroom home. So with 6 people on board and our crew as well, with 12 people in space together, it can get kind of, well, it's actually pretty roomy. It's completely different than the space station or shuttle. Remember I said on that first mission we had 7 people crammed into the size of your kitchen with 1 bathroom. On this mission we had 13 people in a 5-bedroom home, or 12 people, 5-bedroom home, 3 bathrooms. It was great. A lot of room to roam around. Our crew is on the right here in the black shirts, and the space station crew is on the left. And my wife Indra likes to point out that you can easily tell that because we just spent like 2 weeks on the beach in Florida getting ready to go to space. These guys have been up here for a long time. So they're looking a little pasty, but there's 3 Russians right down the middle here, American Ron Garan, Katie Coleman, and another Italian astronaut, Paolo Nespoli. So on our flight, we had the great fortune of having 2 Italians in space at the same time for the duration of our mission, or for most of it. It's not all messing around, or it is some messing around. It's not all work in space. We get some time to mess around. And one of the great things about the space station is you can actually fly in the space station. On the shuttle, you can float. So when we're on the Hubble telescope mission, all we could really do was float in the middle of the mid-deck, and you can move around a little bit, but if you try to fly across the shuttle, you quickly smash into the other wall because it's only 5 feet away or whatever. But on the space station, you can zoom from one end to the other right down the middle of the tunnel that I showed you on the first picture. And so we have a lot of fun, and I'll show a video after I'm done where we get some great shots of us flying down the middle of the thing. And there's another thing that's interesting about this is that when a space shuttle crew gets in orbit, the space station crew who's been there for 3 or 4 or 5 or 6 months gets a big kick out of watching them try to move around, because the new guys don't really have a good sense for how they're going to float in space, what it takes to fly. So when we first get there and we try to fly down the middle, what happens is we take off and we get some sort of strange vector or trajectory, and we end up banging into the ceiling or the wall, and you kind of bounce down the whole thing like a pinball going through a pinball machine. But the space station guys that have been up there for 6 months, they can just push off with a finger and go from one end right down to the other without touching the thing all the way. And it's just because they've been up there practicing for so long. It takes some time to get used to it, but after a while, you really do get pretty good at floating right down the middle. It's a lot of fun. So this is the reason that we flew to space. This is the alpha magnetic spectrometer. And I talked a little bit about exploration and what we use for exploration. We use the Hubble Space Telescope to look into space. We use the Chandra X-ray Observatory. We use satellites, but we also now use this, and this is the alpha magnetic spectrometer. This has been in development for 16 years, worked on by 16 different nations. It's a $2 billion science experiment, and it's really the only reason that STS-134 flew into space, because without the alpha magnetic spectrometer, we would have not had a mission objective. And in spite of the fact that we did 4 spacewalks on our flight and we transferred a lot of hardware to space, we would never have gotten off the ground if it weren't for this scientific objective. And so I'm going to pretend to be an astrophysicist, but I'm really not. So if anybody else is, please forgive me as I talk about this stuff. Hubble can see things in space. It can see the light rays, the cosmic light rays in space. But there is other types of energy and matter in space that we can't see. It's all the blackness out there. And that's why we flew up the alpha magnetic spectrometer, because it's trying to look at charged cosmic rays when it's in space. What we knew from Hubble, what we've learned, is that the universe is accelerating or expanding at an accelerating rate. That's one thing that Hubble taught us. It also taught us that there's got to be something out there. We believe, we postulate, there's something called dark energy that's causing the universe to pull apart the matter. And we also know that there's dark matter out there because there are effects to light rays that we don't understand, and we think it must be caused by things that we can't see. Other forms of matter that are creating gravitational fields that are bending those light rays. So we think that's due to dark matter. And this is just a simplified model indicating that what the postulation is, that the matter is the glue that holds everything together. The energy is the thing that's pulling all those things apart. And we can't image those things. Now I'm going to show a pie chart next, and it's completely not to scale. So for everybody who's a scientist, which is just about everybody, never make a pie chart like this one. But I didn't make this pie chart. I just borrowed it from a believe it or not, from an astrophysicist. So at some point I'll remake it. But the point of this one is that, and what it's trying to illustrate is that we can only actually see 4% of what we believe makes up the universe. So if you take up matter, just matter itself, we believe that 90% of all matter is dark matter. And only a very small portion, so about 10% of matter is things that we can see. Now, if you expand that to the whole composition of the cosmos, we think that 74%, these are all approximations, 74% of what's in the cosmos is what we call dark energy. 22% is dark matter, because we can't see it. We can't see it with Hubble. And only 4% are things that we can see. So all the things that Hubble sees and shows us in the universe, those beautiful images of stars and galaxies, that makes up like 4% of all the matter that we see out there. So that's why we sent the alpha magnetic spectrometer, because we believe it can help us investigate the dark matter, the charged cosmic particles that we can't actually visualize and see. So enough about that. Space is very unique. It's very special. There's a lot of beautiful things to see from space, but one of the best things to see is Earth. And at nighttime, we see 16 sunrises and sunsets, so we see 16 night times each day. We try to take the opportunity to get pictures of the Earth, not only for research, so that we can understand how the Earth is changing through photography from space, but also for just imagination and people's interest on the ground to take images like this to see how the Earth glows at night when we pass overhead is just an amazing sight to see. So I talked about the fact that we did 4 spacewalks on this mission, and I was able to do 3 of them. And I like this picture because it really gives a scope of the scale of the space station. This is Greg Shematoff here on the truss segment, and this is me hanging out on the top of one of our external pallets for experiments. This is the alpha magnetic spectrometer. This is what we placed out on the space station truss. We pulled it out of the Space Shuttle payload bay, and we set it up on the truss for it to live there for the end of the space station's life. But it gives you a good idea of what the scale of the space station is, how large it actually is out there. And in fact, it's really easy to get lost out there when you're doing a spacewalk. When the lights go out and the sun goes behind the Earth, and we just have the little headlights on our visors to help us get around, it's easy to get lost when you're out there because it's so enormous and everything looks the same. At the end of the 4 spacewalks, we proclaimed that the space station assembly was complete. So ours was the second to the last space shuttle mission to space, but it was the last mission that had spacewalkers that were trained on the ground with the shuttle mission to do work. So we still send astronauts out to do spacewalks from the space station, but our mission was the last one where we trained for a year and a half in the neutral buoyancy lab, getting ready for those spacewalks, and as part of the assembly, to complete the assembly of the space station. So after 11 years, with our last spacewalk, with the last component that we left there, we were able to proclaim that the space station assembly was completed. We had some time to relax in space and play a little music up there. Astronauts need to, relieve some stress and tension, and so one of the ways we do that is we get together and play music or have meals together or send email or make phone calls. So we try to find things that we do that are similar to life here on Earth to make it enjoyable to be there for 6 months. And I got to take pictures of things that I liked in space, things that meant a lot to me, things that have an impact on my life that sort of form us and make us who we are. So as a geophysicist and somebody who gets EOS every week, I don't always read them, but I try to read them. I have a big stack on my desk right now. I don't ever throw them away. I always try to get through them, even if just briefly. But anyways, it meant a lot to me to take this to space, and I hope that it makes a connection with many of you here and the rest in the community to realize what we're doing as geoscientists, earth scientists, physicists in general, in the exploration of the planet, and how it's tied in with the human spaceflight exploration program. This is about midway through the mission as we're starting to get ready to come home. The picture was taken to document the program between and the development of the space station with the help of the Space Shuttle. Never in history has a picture been taken of the Space Shuttle docked to the space station. And because the only way this can happen is if there's another spacecraft in the vicinity to take the picture while we're docked, and we're typically the only spacecraft that's coming. And when we're coming to the space station, we're not there yet, so we can't take a picture of us there, right? You get it? But in this case, we had the crew on the space station who, 3 of the crew members had to come home. And they came home on the Soyuz spacecraft. So when they undocked, they spent some time flying around the space station, and they took these pictures of the space shuttle. This is the first time and the last time that the shuttle will ever be photographed docked to the International Space Station. And we were pleased that it was during our mission to document the wonderful program that's existed between these 2 vehicles. After 16 days in space, we came back to the planet Earth. And this is a photo of the re-entry of the space shuttle. You can see the contrail here, which is sort of like the contrail you see of a jet flying overhead in our atmosphere, but this is the contrail of the space shuttle passing into Earth's atmosphere, entry interface we call it, and the hot plasma gas that burns around the vehicle as we heat the gases up so much that they burn, they turn into plasma, and they glow, and they create this contrail. So this is what the space station sees as the space shuttle re-enters Earth's atmosphere. And what's unique about this picture is we don't normally get to see the atmosphere of our Earth, right? It's just there around us, but in this picture, this is the atmosphere of the Earth. And it's just this thin layer, this thin shell that covers the planet. And when you're in space and you look down and you see that thin shell that people analyze and study on the planet and say, well, the atmosphere, what is it? And it's hard to define what it is, but that's what it is. It's just a little layer that protects us from the vacuum and certain death of space. It's like Earth's spacesuit. It's the same spacesuit that we put on when we go outside to do our work. And I don't have to tell you guys how important it is that we try to take care of it and protect our planet, because it really is that fragile. There's not a lot out there. 16 days in space, we landed at the Kennedy Space Center, fortunately. That was the good news for the family. The bad news was we landed at night. And at nighttime, you can't see the space shuttle when it's coming back to the planet because it's dark out and we don't have any lights. If we did have lights, the astronauts inside wouldn't be able to see very well because their eyes wouldn't be acclimated and they want to see the runway real well. So all the families saw, well, during the landing, they could hear us coming, and at the last minute while they're watching the runway, they see the space shuttle just go ripping by, like, whew, and that was it. That's all they saw. So sorry about that, honey. We tried. At least we came back to Florida, but it really was not as much of a sight that we hoped it would be for the people standing by to see us land. This is the crew, happy to be done with our vehicle Endeavour in the background. It was a wonderful flight. We're all smiling because it was a perfect flight for us. We didn't break anything. We didn't lose anything. And we didn't make any mistakes. And that's something that can't be said of all missions. We had 16 packed days of work. Very ambitious effort, but thanks to the leadership and the training we had, it all went quite well for us, and we were just happy to be back on the ground. Now, what's interesting about this photo is that all of us are about ready to fall over in this picture, because when you're in space for 16 days, even a short mission like that, it feels like you just got off of a merry-go-round for a week. And so there's not one of us in this picture that isn't ready to fall over. That's why we're all have our arms around each other, because we're trying to group stabilization here. Okay, that's that mission. Thank you.
Well, geophysics by definition is about exploration and discovery. And if you want to know just how exciting it can be at times, I give you Drew Feustel as Exhibit A. Thank you, Drew, for this fascinating glimpse. And not to where we'll get you those back issues of EOS that you didn't have time to read.